Do I need this thing? Okay, thanks for that intro, and thanks for coming. So my name is Trevor Bacoli. I'm at the University of Waterloo doing my PhD, technically in computer science, but in my research I deal a lot with neuroscientific data, and I've been finding that as I start doing more data analysis programs, I'm starting to find it's much more important to be using physical quantities. And so I'm going to try to show you how you would do that with Python and convince you that it's a good idea so that you do it yourself. So just to orient everyone to make sure we're talking about the same thing, when I talk about a physical quantity, a quantity is just any variable that has both a magnitude, so some kind of number, and an associated unit with it, where the unit kind of ties it to something in the physical world, meters per second, physical. So we usually get introduced to these kind of ideas in high school physics. You know, if you get marks taken off if you don't do your units. But this does have real-world correlates. So this is the Mars Climate Observer. And its subsystems, it's already funny. One of its subsystems was basically gave force in terms of imperial pounds, and one of its other subsystems was trying to interpret that force as newtons. And what happened was although they planned for this trajectory to be out here, it actually turned out being here, which essentially entered Mars's atmosphere and it burnt up, which is unfortunate. Unfortunate, but a good example for those of us that care about units. And I want to try to use Canadian examples wherever possible. And so this is the Gimli glider, another instance of this kind of unit miscalculation, where they calculated the amount of fuel using the pounds per liters conversion factor, when really it should be a kilograms per liter. And so they ran out of fuel, they had to land in Gimli. Very unfortunate, but again, good for me. So let's start doing an actual example using Python. Again, Canadian. So this is from a physics textbook. A hockey puck with mass 0.115 kilograms, moving at 35 meters per second, strikes a rubber octopus thrown on the ice by a fan. The octopus has a mass of 0.265 kilograms, and this combined puck-octopus hybrid slide off together, find their velocity. So from high school physics, we got this law of conservation of momentum. So the momentum before the collision is equal to the momentum after the collision. And momentum is mass times velocity. So we set this up. We've got the mass of the puck and velocity of the puck. The mass of the octopus, velocity of the octopus is equal to their combined mass times their combined velocity. Do a little algebra to rearrange these terms, add in their numbers, and we get that this is 10.6 meters per second. We can easily write a little Python script to do this, set up our 4 variables, just basically transcribe that equation into code, and then when we print that value, we get the same number, approximately 10.6. So, you know, as a scientist, I'm very curious, and so I want to see what happens when I change these numbers. And I know that the fastest slapshot ever recorded was 114 miles per hour. So I can plug that in, do my calculation, and I get another answer, which is 34.5 meters per second. So interesting facts about hockey rinks, they are 26 meters long, which means that this puck is traveling at 1.5 hockey rinks per second, which seems a little fast. Of course, the issue here is that I didn't include my units, so I need to add this conversion factor, converting from miles per hour to meters per second. When I do that, then I get a little bit more of a sane answer of 15.4. And I might decide, well, this is an important thing to do, so I'm going to add in my units in all of my variable declarations. A very noble goal, but this is a horrible way to do it. My analogy is that it's like putting Post-it notes on everything in your junk drawer. You still got a drawer full of junk. So the way to do it in science is to keep track of your units with your magnitudes. And there are a number of Python packages for doing this. I've listed 7, but this is not a comprehensive list. And basically they all have their own little niches that they're good at. But what I'm going to suggest is that the quantities package is my preferred package for doing physical quantities for 3 reasons. 1, the syntax is very nice. It's very easy to use. 2 is that it does dimensional analysis kind of built in. And 3 is that it integrates very well with the rest of the scientific Python stack. So to take that same example and add quantities to it, I'm going to import the quantities package. We tend to use this short form of PQ for physical quantities or Python quantities. I just multiply all of my magnitudes by the unit that that's corresponding to them. So kilograms for my masses, meters per second for my velocities, and then when I print out my final answer, it tells me what unit this is in, which is great. So now when I do this example of changing this to the fastest slapshot in the world, I note that I get the same answer, but now I know that this is in miles per hour. And so I can then convert this to whatever units I want using this rescale function. And just because I tend to think of things in kilometers per hour, I'm going to rescale it in terms of kilometers per hour. And so I know now that this is 55.6 kilometers an hour. So, urban driving speed. I also happen to know, Canada's kind of weird with its supposed use of the metric system. The NHL actually defines the mass of a puck to be in ounces, so it's actually 6 ounces. And so if I make this puck an actual, official weight puck, then if this slapshot had hit this rubber octopus, now I know that it would have gone 72 kilometers per hour. So it's pretty cool. So the other thing that I talked about is dimensional analysis. So the idea here is that if you take out the magnitudes from your equation, you should be able to figure out, it's kind of like an error checking thing where you can figure out what the answer, you can make sure that your formula, that the units work. So you can add like units together, cancel units out. So this equation is proper. If we had forgotten the units in our octopus velocity because it's 0, you're just like, who cares? Well, quantities cares, and it tells you that it's unable to convert between these two units. So basically the mass of the puck and velocity of the puck is in ounces times miles per hour, but this is only in kilograms, and so it can't convert them, can't add them together. So this is all kind of built in. Another reason why you might want to use quantities. Sometimes you'll be working with quantities that aren't already defined. So meters, kilograms, that kind of stuff, we know about that. But there are other units that you might use in your domain that aren't in quantities yet. So you can define your own units using this unit quantity class. Just give it the name of the units and then a definition, which is kind of how it maps to an existing quantity. So I'll give another Canadian example. Suppose that there are 250 people at PyCon Canada, which I think is relatively accurate. And on average, we consume about 200 milliliters of milk. The question, of course, is how many bags of milk do we need? So in order to answer this question, I'm going to define a new unit called milk bags, which is 4/3 of a liter, which is true. I don't know if you've done this calculation before, but it's 4/3 of a liter. And I'm going to say that a person is just some dimensionless quantity. We all don't have dimensions. And what I need is 200 milliliters per person. I multiply that by the number of people, 250. When I print out my need, I get that we need 50,000 milliliters of milk. I can rescale that to be in terms of liters, which is just easier for me to reason about. And I can do the same rescale function and give it my new unit of bags to see that I need 37.5 milk bags. Of course, we can't buy fractional bags. But fortunately, since quantities integrates with the rest of the scientific Python stack easily, we can use NumPy's kind of number crunching abilities to rescale this and then take the ceiling. We get 38 milk bags. So these are kind of toy examples to hopefully give you an idea of the syntax and to convince you that it's not very difficult to include units, and you get a lot of these tangible benefits. But I want to give an example from my own research. So I work with neuroscientific data, and this is kind of an example of that. This is called a spike raster. So experimental scientists will record the activity of neurons over some time frame. Each one of these little lines is a spike, so it's a neuron firing an action potential, and we can look at how these action potentials, when they happen over time. Each one of these rows represents one neuron. And typically what happens is we have some salient behavioral event occur at a particular time. So in this case, we have an event happening at about 11 seconds. And what we want to look at is the neural activity kind of before and after that event. So this kind of blue shaded region is the region of interest. We call it the peri-event epoch. I never know how to pronounce that word. And So if we just take this little section, then we get this kind of subset of our spike trains that we can plot. So when I first got into neuroscience, I was looking at some legacy code, all of which is kind of in MATLAB. Neuroscience still uses MATLAB. Not my problem, or not my, I didn't do it, just use it. So this is an example of some kind of legacy code from MATLAB. So you use the load spikes function to load up spikes from some comma separated value file. You bin those spikes, and then you do this kind of ugly magic indexing. Round brackets are array indexes in MATLAB, by the way. So you're just indexing into this array using magic numbers, which hurts me to my core. And so what this ends up looking like is that when you bin spikes in this way, you no longer have the exact timestamps of these spikes. You just have kind of these time bins, and you know how many spikes occurred within this time bin. And so if we zoom in on this peri-event region, we get this kind of pixelated image. The pixelation really actually isn't the problem. The problem, well, there are many problems, but one problem is that we don't know if these spikes are represented in seconds or milliseconds. And neuroscience is an interesting domain because we do these experiments over many seconds, minutes, hours, but we can get granularity to the millisecond. So sometimes it'll represent it in seconds and sometimes in milliseconds. We don't know the size of our bins when we bin these spikes, unless we go into this bin spikes function and figure it out. And even if we're okay with these magic indices here, we don't know when the actual event occurred within this peri-event epoch. So I wrote my own little code to do this using quantities. And so what it looks like here, or what my code looks like, is that I do the same load spikes function, but then I explicitly tell my code what unit these are in. So in this case, it's in seconds. I say that my event happens at 11 seconds. I'm looking at the window 0.5 seconds to 2 seconds before and after. And then I just do this time slice function, which could be very complicated, but because we have this nice NumPy and all these other utilities, it's just actually an array index, an index into the spikes ND array. So we just take every spike that comes after the start and before the end. If I happens to want to use my analysis code in terms of milliseconds, I can just rescale this. I don't need to change my event or my window. This time slice function works the same just out of the box, which is very convenient, especially when you're kind of changing the event that you're looking at. You don't have to make a lot of changes to the code. You just have to change this event, and you get all this kind of for free. And then, there are situations in which you want to bin spikes. So if I do want to bin spikes, I can do it with this simple 3-line function, call it with another line, and I have in here that I have to be explicit about my bin size. So having quantities makes it possible to do these kinds of real-world research. It allows me to solve these real-world research problems pretty easily and very extensively, and I would argue that it's pretty readable. So if you want to explore this code, it's on a GitHub repository, Tibicoli, PyCon CA 2012. There's an IPython notebook that has all these plot generation scripts. And in order to do that, you'll have to pip install quantities or easy install quantities if you must. The documentation's here. And yeah, I hope you're convinced to use quantities in your research or just your regular programming. Thanks for listening.
And use the mic.
Okay, mic for here?
There's a button on it, yeah, push that button.
Okay. Okay, yes, if anybody has questions, we've got a mic here. We can probably take one or two before the break. Can you come on up?
I can also just repeat the question if you want to yell it.
Yeah.
How does it mesh with the decimals module?
How well does it mesh with the decimals module? Good question. I have no idea. I've never actually used the decimals module. Could you give me like a little code snippet that I can type in and see?
Import decimals.
Uppercase?
No, it's decimal.
That's like singular. Lowercase singular.
This is how little I use the decimal class.
It's fixed point.
Okay.
It's, what's the fancy term?
Floating point number.
Mhm.
Fixed.
So can I just say like,
It's decimal dot decimal capital D. Oh yeah, got it.
and then put a number in here?
Yeah, don't put a string. It gets complained.
Don't put a floating point.
Put a string.
Oh, gotcha.
It's not precise.
Live demos, that's why I didn't do it. So we'll say A equals that, A times seconds. Apparently it does not like it very much. So, sorry. However, you know, this is all open source, so you can write a little patch for it. It's perfect. Perfect project for you to work on. Yep.
For your dimensionless objects,
Yeah.
could you put dependencies on them, like constraints of some sort?
So yeah, the question is about the dimensionless quantities. Can you put constraints? So there are kind of built-in constraints that if you try to use it as just a regular number, it will usually complain. But if you subclass, so if you make a unit that is, so that person's unit, when you make the person's unit, it's no longer compatible with other dimensionless quantities. I mean, it is, but it'll be explicit about it. So if you have like people divided by whatever other dimensionless radians, people divided by radians, then it'll tell you, you know, that this is people over radians and not just people. Yep.
Yeah, hi, I'm just wondering about the overhead, because so if you're attaching this unit thing to every single piece of data, you have lots of data.
Mhm.
So I'm thinking, does it work for large things, or is there maybe a way to turn it off, like once you finish debugging?
Yep. So the question is about the overhead of using quantities versus not using quantities. And so this is the real advantage of quantities, is that the quantities class is actually a subclass of NumPy's ND array. So, you know, NumPy's ND array is just, it basically lets you work with a huge chunk of numbers at once, as if they were one object. So if you want to add 5 to a NumPy ND array, it doesn't loop over it, it just does it all kind of, well, it loops over it in C, which is better. And so because it's a subclass of that, there is a little bit of overhead, but not that much, and not an appreciable amount of overhead if you're doing something that requires you to have a huge NumPy ND array anyway. Ooh.
So we can probably take one more really quick question. Is anyone? No?
Yep.
Well, I quickly played around with it, and it doesn't collapse quantities
Oh,
together.
yeah.
Which is my first, because when I used Boost in C++,
Mhm.
I was doing it for like Newton meters for torque.
Yeah.
And it was constantly converting it to like joules.
Right. So, so the question is about collapsing these units. So there is, you do actually have this. I just didn't do it as an example. So if we have, this is going to be a terrible example now that I think about it. But if you have something like seconds over milliseconds, this is not going to work. But seconds squared over milliseconds. So it gives you that. You can do a dot simplified, and it gives you the simplified version. Yeah. So it does do that. Yeah.
Okay, thanks a lot,
All
Charles.
right. Thanks.